Okay, hello everybody. Thank you very much for your time. I have many slides, so I have to be very fast. Here is an introduction to the medical AI. There are some notices I should mention. There is no conflict of interest. All topics and presentation has been modified uh, for physician without any experience in computer and maths. So they are not accurate as a matter of the computer science, but they are just conceptual review regarding the most common medical AI applications. Also, only radiology related topics are going to be covered in this presentation. The goal of this presentation is just to scratch the surface of medical AI, and hopefully I can help you a little bit to understand the medical AI papers and literature. So first of all, let's start with a few terms and terminology. What is the meaning of intelligence? What is the natural intelligence versus machine intelligence? Intelligence is considered to be the ability of the learn or understand or deal with the new situations and to apply knowledge and to change the environment or think abstractly. In this context, intelligence contains many topics, including logic thinking, critical thinking, learning, understanding, reasoning, planning, problem solving, awareness, and emotional creativity. Human intelligence is considered to be general. That means at this time, you look at one picture, you understand it, then you speak, then you write, and your brain is able to function on different topics and different fields. So this is called the general intelligence. In the other hand, we have artificial intelligence, that they are the capability of the machines to mimic the intelligence of human. AI at this time is very narrow. That means it is not generalized, it's not general AI. So that means when you train and develop one AI application, eventually it is able to do a very narrow task. It is not general at this time. History of AI, it's not a very new concept. It starts from the 1940s and 50s. The basic concepts of the AI were developed in 1940s. In 1956, there are the first movements regarding the artificial intelligence. After that, nothing happened. We call it AI winter period. Then in 1990s and early 2000, we have the time of development of machine learning. However, after a few years, again, we have a winter regarding the AI application. Not much happened. The new era of the AI started in 2012. And at that time, one convolutional neural network by name of AlexNet was able to defeat the human in the image recognition. And we are at the era of the third spring of AI. Improvement of AI depends on big data sets, which these days are available. Also very robust GPUs and fast GPUs. So we are at the third AI spring. Who knows what happens? We may continue in progressive regarding the AI. We may have the third winter time. So we should wait and see what's going to happen for the AI. So you can see that it starts with 1950 and 1960, not much progression. Again, in 20 and about the first years of this century by the expert system and machine learning. And we are at this point right now. The effect of social media and social excitement is much more than the real world. And here is the review regarding the pioneers and the achievements of the AI. Machine learning, support vector machine was a very big achievement regarding the AI. Deep nets and then AlexNet in 2012, which is the beginning of the new era for AI. So what is the current momentum of AI? Having large data set, having robust GPU, ends in numerous publications. These are for the comparison for 3 years of PubMed publication for artificial intelligence and machine learning. As you can see, every year we are publishing more and more papers. These days, without having basic knowledge of the artificial intelligence, you cannot understand many medical literature. So that's the thing, that we should be familiar with the basic concepts of the artificial intelligence. The main question for us as a human physician is that AI is going to replace us or no. So at this time, it is very narrow, as I said, or it's weak. It is able to do a very narrow task. It is not generalized AI at this time. So to compete to the general intelligence of human, the AI should be artificial general intelligence or super intelligence. Super intelligence means the AI which is even better than the brightest human minds. At this time, we are far away from this point. So it is very unlikely that during our career and our life expectancy, we see that complete replacement of the AI, human by AI, but we should learn how to use it. AI would be a very good tool in our hand for further progression and research. Okay, a few terms regarding machine learning and artificial intelligence. In the world of AI, machine means any computer program or codes. Traditionally, if you provide a code with same data for 100 times, for example, you get exactly the same result for the 100 times. This is the traditional coding. However, the machine learning is the program and coding that they are able to write their own codes, and they can improve over the time by having more and more data. On the other hand, machine learning enables the computer and code to write their own programs. What is the deep learning? Deep learning is a type of the machine learning, is a subfield of machine learning. The goal of deep learning is to mimic the behavior of neurons in human brain. It contains the most important part of the deep learning, which is artificial neural networks. At this time, deep learning is very robust for detect objection, for image classification, segmentation, for speech recognition, translation, and decision making with classification. So at this time, the most robust application of artificial intelligence is neural networks belongs to the deep learning. So here you can see the location of these sciences. Artificial intelligence is a large basket. One subfield is machine learning. Deep learning is a subfield of machine learning. All of these sciences have overlap with data science, but they are not purely data science. They have many more things out of the data science. The other term you should be familiar with is the feature. In machine learning and artificial intelligence, feature is a very common term to be used. In order to feed the code and the computer with the medical data, many old and narrow artificial intelligence models are not able to work with the raw data. In order to work with the raw data, first of all, you should convert the raw data to something which is understandable for the code and the software. These things that are understandable to the code and machine are called feature. For example, in this patient with the chest CT and the mass in the lung, for the most of the old narrow machine learning models, you cannot use the raw image for any classification. You have to convert it to things that is understandable for the code. For example, the size of nodule in millimeter, speculation, yes or no, presence of calcification, yes or no, and so on. So the act of converting the raw data to the things that are understandable to the machine is called feature extraction. And here I should say that we have two large classes of the feature. We have numerical, we have categorical. Numerical, the size of, for example, the size of nodule in millimeter, it is a number, it's a continuous feature. We have got categorical, for example, yes or no in speculation, or the grade of neoplasm, grade 1, 2, 3, or 4. These are categorical features. You should be familiar with the type of feature because based on the target feature and predicting feature, we have to develop specific models. Some models are not able to work on the numerical feature and the vice versa. Some other models are not able to work with the categorical features. So remember, this is the feature, this is the feature extraction. In deep learning, the models are able to accept the raw data itself. And that's one advantage of the deep learning in comparison to the shallow learning models. Okay, and here is the value of the deep learning. By using the deep learning, there is no need to do feature extraction and feature engineering. The model itself is able to extract useful and predictive feature from the raw data, for example, this CT scan, and it can develop a machine learning for prediction regarding the malignancy or benign mass of the nodule. This act is called feature learning or representation learning. So for the shallow learning, we have feature extraction. For the deep learning, the model is able to do it itself by the name of feature learning or representation learning. So beside these categories, we have three very important subfields of machine learning. We have got unsupervised machine learning. We have got supervised and semi-supervised. In unsupervised machine learning, we provide the data. We provide the machine and code with the data, which are not labeled. They are just data. The machine should work on them and cluster and classify the data onto different subsets. In the supervised machine learning, the data is known. They are labeled by human before the machine learning development. So the code and the software receives the hit from the human. The semi-supervised machine learning is something in between, which I'm going to explain in a few minutes. The unsupervised machine learning, as I said, there is no hint from the human from outside. There are different application of the unsupervised learning. The most common in the medicine are clustering algorithm, dimensionality reduction, models. So these two are the most important application of the unsupervised machine learning in the field of medicine. Let's have a look at the clustering. Suppose you have a very large data set, different features, different shape, different colors. We are going to feed the data set to the machine learning model for clustering. The model is going to work on the data itself without any help from outside. Then it's going to classify or cluster these data into different subsets and classes. As you can see, there is no single answer for this task. The model can classify the data based on the color, based on the shape, or based on the roundness. So here is the one example of the clustering. Suppose you have a sample from the peripheral blood smear, and you provide the software with the images. After working with hundreds of the samples, over the time, the software is going to understand that some shapes are small and red. It doesn't know that those are RBC. Some of them are larger and white color. They are white BC. Some of them are tiny and irregular. They are platelet. The software does not know the name of the RBC, white BC, or platelet, but over the time, we can learn to classify those shape and features from each other to different classes. Then the human and the researcher can use these classes for further development. The second important application of the shallow learner and unsupervised machine learning in medicine is the dimensionality reduction applications. These days, we are able to extract hundreds and thousands of the features from medical data. For example, again, CT scan from the chest with the lung mass. If you segment the mass, the softwares these days easily can extract hundreds and thousands of the features. It is very well known that if you develop machine learning on thousands of the features, the model is going to be perfect in your training data set. So while you are working on your data and working on your machine learning model, it's going to perfect more than 99% accuracy. However, if you use this terrain model in the real world, you can see that performance is very poor. That's because of the fact of overfitting. Overfitting is the thing that your model is going to be very perfect and very accurate in the training session, but it is very poor in the real world. To avoid the overfitting, and to improve the application and accuracy of the model in the real world, one strategy is using only the most important and predictive features to develop the machine learning. That means from thousands of the features, you should find the most predictive feature and select them and build your machine learning model on top of these features only. This act is calling feature selection, or the other term in the machine learning is dimensional reduction. Dimensional reduction is a way to make the data simple, to reduce the redundant feature, and to keep the most important feature for further AI development. Okay, so we reviewed the unsupervised machine learning and deep learning very quickly. The next category is supervised learning. In supervised learning, we help the code and the software before starting. That means if you have a data set here, for example, a large data set from the chest X-ray, first of all, we hire a human radiologist to label the X-rays, to label, for example, the masses, and this one, and this one as a red color, and the label the normal chest X-ray to the blue color. That means the data is now labeled and now. Then we are going to feed the data set to the model. The model is going to learn on top of these features and label data, and then we can implement the terrain model in the real world. This is the concept of the supervised machine learning, very common application and pipeline in the radiology. In the radiology, image classification is very important, and it is one of the most usable pipelines for development of any kind of AI for radiology application. The next subtype of the supervised machine learning is classification. So here is some important application of the supervised machine learning. You can call them as classification, regression, and segmentation. So in radiology, classification is very important in supervised machine learning. For example, here, if the model is going to predict the diagnosis of the new chest X-ray as positive for lung mass versus normal chest X-ray, that's the classification text. It's going to divide the new data or new patient to one of these two classes, either tumor or normal chest X-ray. Sometimes the task is regression. What is the difference between the regression or classification? Classification, the output and the predicted target is going to be a categorical. It's going to classify it as 0 or 1, benign or malignant, or so on. In the regression, the target is a number. For example, we feed an algorithm with the chest CT, and we ask it to calculate the volume of the lung mass. The output and the target here is the volume. It's a continuous and numerical data. When the output is a numerical continuous target, the task is called regression. There you have to select the suitable models for the classification or regression. Otherwise, you cannot develop your AI models for classification and regression. The other very common application in the supervised machine learning in radiology is segmentation. Segmentation is marking the area of lesion or area of interest with different color or contouring. Some people consider segmentation as a subtype of classification. For example, if you consider every single pixel of this picture, you can classify every single pixel of this picture to the mass or non-mass. And that's the equal of the segmentation if you want to segment the lung mass. For segmentation, there are also different subtypes of segmentation. You can only segment one tissue. Here, for example, I want to segment only the brain tissue with black color. That means everything else, including the bone, the CSF, or hematoma, is going to be another color beside the black color. You can do the semantic segmentation. In semantic segmentation, every type of tissue is going to have different color. Here, for example, the bone is yellow, CSF is blue, blood is green, and this brain material itself is black. So that's one type of segmentation. This is the other type of semantic segmentation. Okay, let's review the AI pipeline. To develop an AI model, we have to go through a pipeline. The most important part of AI development is training. In training, you can consider the software or AI model as a radio station receiver with a bunch of buttons which you can adjust and modify them to fine-tune your receiver to have a better voice from the radio station. When you feed the software with your input and raw data, you want to get prediction regarding the classification of data. In this example, data are either red crosses or blue. The task of training the software or model is to fine-tune every single button in this box in the way that the software is able to draw the most accurate line between the blue versus red signs in this picture. That's the conceptual understanding of the training in the machine learning. On the other hand, it is not correct in the real world. One major disadvantage of many artificial intelligence models is that you cannot explain the process of decision-making in the artificial intelligence. And in medicine is especially important. In many AI models, you cannot look back and see why this decision or classification has been done. So this is the concept of black box in the artificial intelligence in medicine. These days, there are many researchers targeting this weakness. They are going to develop more transplant machine learning model, which can be interpreted after prediction. These days, still most of the AI models are essentially black box. So you cannot explain why the decision was made in this situation. Okay, let's review the pipeline. In the pipeline of machine learning, in this case, which is supervised machine learning, very common approach for radiology, we are going to have a very large data set containing hundreds and thousands of the images. Then we are going to do the pre-processing. We are going to review the images. We are going to exclude images with motion and poor quality and so on. Then we have got a clear data set. Then we are going to hire a human to label the data as a positive or negative. This part is very time consuming, very expensive, because every single data should be identified and labeled by the human. Then traditionally, we are going to divide the data set into two large classes. Usually 80% of data set goes to the training data, 20% is going to test data. We don't touch the test data. We keep it in the safe location. We don't look at them. But for the training data, we train our model on these 80% of patients. We evaluate, we have some strategy to evaluate the performance of the training. I'm going to review it in a few seconds with you. But eventually, when the model is trained, and we think that the performance is okay in the training data, then we are going to test it in our data set and see how is the performance of the trained model on the test data set. If the performance is good, it's high, now we can use it for the real application, for clinical application. Many times the performance is not good, so you have to stop the development, or you have to fix some problem in this pipeline to improve the quality of your machine learning and AI. So here is that 80-20%. Usually 80% of data goes to the training data. 20% is untouched. We save it for the test. Within the 80% of training, there is a smaller subset by name of validation. We use validation to evaluate the training while we are in the training process itself. Training process in machine learning, especially for image classification, is a time consuming. Sometimes it takes days and weeks. You should have something to evaluate the training. If the training is not efficient at all, at some point you should stop it very quickly, otherwise you will lose your resources and your time. So the validation data is a subset, a part of training data, which is going to be used during the training the data and to see if you are going to the correct direction or no. If even in the training session, the validation data says that training is not efficient at all, then we are going to stop our development because it's not going to work. Okay, so we reviewed the unsupervised and supervised machine learning. Let's have a look at the semi-supervised machine learning very quickly. It is very good application when you have a very large data set. Suppose you have 100,000 patients, just medical record, and you have very limited resources. You cannot hire the physician to identify and label each patient manually. But you can, for example, label, maybe you say 100 patients. So very large data set, very few labeled data. In this semi-supervised, you are going to start with unsupervised machine learning. You provide the machine time and space to work on the large data set and cluster the data set into several more uniform patients. Then when the machine is able to classify the large data to the smaller homogeneous data sets, that's the time that you can use your few labeled data, and it's going to help you to develop a machine learning while you have a very limited resources. So large data set, you provide the data set to the unsupervised clustering. Over the time, for example, you have a large data set of GBM and brain metastases. Over the time, the clustering algorithm understands that some people, they have a single large mass with central lack of enhancement and necrosis. Other people, they have multiple enhancing lesions in the corticospinal gray white matter junction with severe edema. The machine does not know this is GBM or this is metastasis. It has no idea about the GBM or metastasis. But now it can cluster your data set into more homogeneous classes. One class, multiple lesion, the other class, single lesion, but larger. Now this is the time that you can provide the model with the label data and say the model, look at my labels. When there are multiple lesions, this is the term of metastasis. When there is single lesion, this is GBM. At this time, the model can be trained for classification of the GBM versus metastasis from the large data set while you have very few labeled data. And this is semi-supervised machine learning. So if you develop a machine learning, all the time you are fighting with the overfitting. Overfitting is the most important concept in the machine learning. Let's see what is overfitting. You can measure the accuracy of the developed model in two ways. You can evaluate it in the internal data set. For example, when you train the model in the data set from your university, then you can test it on your data set and see how is the performance. The next thing is test it in real life. Ask your friend to send you a large data set from another university and run your model on those data, or run your model in the future in the prospective study and see how is the performance of the model in the real world. In many situations, you can see the model is perfect in your training data, but in real world, it's very poor in performance. This paradox is called overfitting. There are several reasons that the overfitting happens. The most important reasons that the overfitting happens is that you use a small data set to train it, or the model is very strong. When the data set is very small, or the model is strong, essentially your model memorizes the data. That's the reason that in your internal data, when you evaluate the model in your data set data, performance is close to 100%. The model is memorizing the data. It's not learning any useful feature. It just memorized the data. While you provide the model with the real world, that memorized data has no rule, that it has no predictive power, so the accuracy is going to be very low. And finally, when your design and the pipeline is weak, you see that the performance of model is high in the training, but with very poor performance in real. So let's look at the underfitting. That's the opposite of the overfitting. Underfitting is a less common problem in the machine learning, but still you should know it. Underfitting happens when the model itself is very weak. For example, for the image classification, which is very robust and difficult task for the machine learning, if you use basic support vector machine, regardless of the number of the data, the size of the data set, and the pipeline you use, the performance is always very poor because support vector machine is not able to capture predictive feature from the very complex image classification. So here is the application and the curve during the training session. If you remember from this slide, let me come back. Oh, sorry. I was going to this one. Remember, for the training and validation, both of them belong to the training session. We use a part of the training by name of validation to see how is the progression of the training. So when you are training the machine learning model, you look at this curve, and this is the thing that we look for. If you provide the model with more and more data over the time, you should see interval increase the performance of the model in the training data as well as validation. However, sometimes you see that over the time, the training accuracy is getting better and better. Over the time, validation remains the same or it drops. This is overfitting. That means your model is memorizing the data. It's not learning. Your model is too strong, your data set is too small, or your design is weak. This model is going to be very good for training session. You can easily publish it in the literature and journal. It has no performance in real world. Validation is going to say that there is overfitting. You should either increase the size of data set or you should fix the model. That's the concept of overfitting. You see that over the time, even the training is not getting better. Training and validation are both in poor zone in the performance. That means the model itself is not good enough. You should replace the model with something else which is more accurate. Okay, regularization. Regularization always comes with the overfitting. Every time you are going to fight against the overfitting, you are going to improve the regularization and generalization. So all of the techniques and strategies in the machine learning that they are going to improve the performance of the machine learning in the real world with decreasing overfitting and improving the generalization is called regularization. So regularization is a big part of machine learning. There are some techniques to improve generalization of the model for the real world. In the radiology, especially convolutional neural network, there are some strategies belong to regularization. Early stopping is one of them. Shuffling the data and mixing the data and playing with the learning rate are the most common strategies of the regularization in the convolutional neural network for the image classification in radiology. Okay, now let's look at the evaluation of the model. Every time you have got an AI model in medicine, you should have a way to evaluate the performance. There are two types of evaluation. You can evaluate a model internally during the training session. The most important indicator of the accuracy within the internal model is the cost function. I'm going to explain it a little bit more in a few seconds. In the real world, you can use the standard statistical tests such as specificity, sensitivity, accuracy, and so on. So we have internal metrics, we have external metrics. Internal metrics is for the phase of development. External metrics are for the phase of real-world application of AI. Internal metrics, we use them during the process of learning session and AI development. The most important one, as I said, is loss or cost function. And that's the concept of cost function. Please remember this concept. The entire training depends on understanding of this concept. For example, suppose we are going to train a software to classify these images. We have one class of red crosses. The second class is blue sign. The machine is going to train how to classify them. In the other hand, or on the other word, the machine is going to be to learn how to derive the best line to separate these signs from each other. To do that, and almost all of the AI models to draw a line, first of all, the model is going to draw a random line. So the model is going to start with one just guess, one estimation. Say, for example, here, it's going to draw a line. When this line is drawn, then the model is going to calculate the distance between each sample and this line. Then for the next step, it's going to guess another line, for example, this one. Then again, it's going to calculate the distance between all of these numbers and this line. At this point, the software is going to compare the distance between the sides, this sign versus this line and that line. If the distance is going to be decreased and shrinking, that means the guess was in the correct direction. So the third guess is going to be the same pathway. So that means the software is going to come downside little by little until the point that when it draws this line and calculate the distance, and when it guess another point and again calculate the distance between the sign and that line, it sees that the distance is actually getting larger, the distance between the line and the sign. At this point, the software understands that this point and this line is the best dividing line between these two signs. That's the same as going downside from the peak of mountain to the valley. This is the concept of cost function. This area is called error surface. That's the difference between the estimation done by the software and the real value. So for every estimation, the software is going to compare it to the ground truth and the real value and the label data, and it's going to evaluate if the changes are going in the correct direction or in the false direction. And here you can learn the concept of the rate of learning. For the coming downside from here to this area with minimum difference, you can choose very small steps, little by little by little. It takes a lot of time. The learning rate is very slow. But sometimes you can choose the very large step. You can jump here, you can jump here, you can jump here. In this way, the learning rate is very fast and very high. There are some advantage or disadvantage. When you choose very slower learning rate, that means it's very time consuming. Training is going to be very time consuming, and you have to have the resources to train your model. When you use very large steps, training is very fast, but there is one disadvantage. For example, suppose I am here, I choose this line, this step. So what would be the next step? It jumps here, then jumps back, jumps here, jumps back, jumps here. And you never reach the maximum, the optimum location of the training. And that's the disadvantage of selecting the very fast learning speed. There is some advantage and disadvantage of the selecting the learning speed. The learning speed depends on you. You can choose your learning rate yourself. You can choose very fast or very slow, depend on your situation and your pipeline. Okay, that was the internal metric for cost function. That's the way that software learns how to train, how to be trained, and learns how is the direction of training. If it's not going toward the optimal direction, the software is able to correct it. External metric is the statistical test. You can use the confusion matrix, the same as you are all familiar with the true positive and true negative. We can use sensitivity. Sometimes we call recall in the AI for the term sensitivity. For specificity, sometimes we'll use selectivity. They are the same for AI literature. Accuracy, positive predictive value, negative predictive value, and F1 score, the same as biostatics you are familiar. Also, there are some external metrics which are not really familiar in the biostatics. One of them is ROC, or receiver operation characteristics. Usually we use this one to find the best model for classification. That's the correlation between the sensitivity and 1 minus specificity. The AUC of 0.5 is useless because the accuracy is equal to the head and tail. If you toss head and tail, the accuracy is 50%. The higher the AUC and the closer the AUC to the 1, the better the prediction. The closer to the 0.5 is the worse the prediction of the model. So the ROC curve is an indicator of the AUC. It is going to evaluate the relationship between true positive rate versus false positive rate. And actually, the ROC curve is the relationship between the true positive versus false positive rate on different classification thresholds. For example, here is the curve. As you can see, the curves closer to the number 1, the better the prediction. Closer to the number of the 50 or 45-degree angle of the line, the worse the prediction. And all of these dots are one threshold of classification. So we are going to evaluate the relationship of the true positive versus false positive rate. So ROC is also very common indicator for evaluation of performance of machine learning in the medical AI. The next external metric is DICE score, very common indicator for segmentation in radiology. Suppose you want to segment a GBM, so you hire a human radiologist to segment the GBM manually. Then you develop a model to segment the GBM, and you have this segmentation. One way to evaluate the accuracy of segmentation of this area is compared to the human segmentation. And this is the formula. 2 multiplied by share area of these 2 segmentation, divide by this one plus this one. You can see in the perfect situation, when there is 100% coverage between these 2 segmentation, this number is 1. 2 multiple 1 is equal 2. 1 plus 1 is equal 1. So the number 1 is DICE score of perfect segmentation. The higher the DICE score, the better the segmentation accuracy in the radiology. Those in external metrics are essentially very good for classification approaches. For the regression problem, when the output is the number, they do not work. The most important metric for the regression model is the MSE, mean square error, which is the difference between the prediction and real world value. Okay, a few challenges. If you are dealing with a small data set, which is very common in medicine, those metrics usually developed for the large data set of hundreds of thousands. But if you have only 100 data, you have only 100 patients. What if you divide the patients to the training and test, all of the positive patients go to the test just by chance, or all of them by chance go to the validation. You may have very bad machine learning in this situation because you don't have any accurate test to measure the performance of this model. In this field, you have cross-validation. when you want to do cross-validation and when you have small data set, you choose a part of data as a test, you train the model on the train and validation, and you get one performance here, for example, accuracy of 90%. You repeat everything, but this time the test data is not the same as that one. It's slightly different. Also, the trained data set is different, and so on. You are going to repeat this process for k times, and then the entire accuracy of all of this model is going to be the overall performance. This is one strategy to avoid random changes for the small data set for the traditional approach for the machine learning. This is k-fold cross-validation. Traditionally, 5-fold and 10-fold cross-validation is the most common metric for the medical AI. So 5-fold cross-validation, that means you repeat training and test for 5 times. Every time you change the data set and training, and then you evaluate the average accuracy and performance of all 5 different models. Then you are going to report this one as the final accuracy. One extreme subtype of cross-validation is leave one out cross-validation. Suppose we have only 20 patients. We have a very small data set. So far, most of the models are not able to work with very small data set, but by using this leave one out cross-validation, you can train your model on very small data set. For 20 patients, this time you are going to keep one patient and train on other 90 patients. You are going to repeat this one for 20 times, and every time you select and keep one patient for test. After training and testing for 20 times, you are going to report the average accuracy as the final accuracy. By general criteria, the smallest data set that you can run an AI model or radiomic model in radiology is 24 patients. You have to have at least 20 patients for the false and for the positive, and 12 patients for the negative. For example, 12 cancer, 12 normal chest X-ray. That's the minimum size of the data set. So if you have 20 patients, 12 by 12, that means 24 patients totally. You can run the basic, very basic, simple machine learning model by using the leave one out cross-validation technique. And let's talk about the external data set. Until 2-3 years ago, it was very easy to have a data set in local data set in your hospital here at UAB. Labeling, supervised machine learning, training, testing, and if you get a high performance, it's very easy to publish your data. However, over the time, we saw that there are many published data in literature, most of them from the engineer group. They are perfect in the paper, but when you run it in the real world, they are very poor in performance. And that's the value of external data set. These days, many journals, they don't publish any AI medicine paper unless you have external data set. So external data set, that means when you have a very good performance in your data, you cannot stop. You should collect the data from the other universities, for example, here from the University of Florida, then run your model on this new data set. If you have a robust performance, that's a very good thing in favor of your model. Now you will be much more confident regarding the performance of your model. And it is very high likely that your model is not going to work only on paper. It's going to work in the real world as well. And if you run this test, you will have a much higher chance of being accepted if you submit your paper in the journals. And that's the value of external data. So that's the end of basic concept. Let's review the shallow learning models. Shallow models in AI are old, but they are big, but they are not weak. Shallow does not mean weak. Actually, some of them are very fast, very cheap, and very robust. And you should know them because they are backbone of the deep learning and neural network. PCA, principal component analysis, is a very old shallow learning. It belongs to the unsupervised machine learning, and it's very good algorithm for the removing the redundant data and for the feature selection. For example, here I have a data. It has 100 by 100 pixel. It can be easily presented with 10,000 pixel and data set, which is very huge. But you can present this data just by the size of the shape of the object, the size of it, the image inside, and the color of the image inside. You can see you can convert this object only to the 5 feature rather than 10,000 feature. This is feature selection or dimensionality reduction. PCA is very important in this field. In the other word,
this actually might be a good time to take just a brief break.
Sure.
Some analysts may need to return to service at 1 or after 1. But yeah, so we can take a 5-minute break here. Anyone who needs to go back to service, please feel free to go. We'll have these recorded and on YouTube and on our website, hopefully within the next week.
Okay, thank you. So if I continue, let me. Okay, thank you. So for example, you have a 3D object, an egg here. PCA is application to present it on the paper in 2D. And that's the value of the dimensional reduction algorithm. In the radiology, radiomics is a hot topic in research and publication. In radiomics, we extract hundreds and thousands of the feature. Again, if you build a machine learning on top of thousands of the feature, you will have the overfitting. But when you run the PCA, you select the most important feature, the model is going to be very predictive in real world as well. KNN is another robust shallow learning. It belongs to the unsupervised machine learning. And it's the model to compare the new data set with the large data set and to return the most similar patients from that data set. For example, if you update X-ray from the hand and chest to the KNN and ask the KNN to return the 3 most similar patients, you see that the KNN is returning 3 patients. 2 of them are rheumatoid arthritis. The 3rd one is SLE. That means, on average, the most likely predictive and the diagnosis for this patient is RA. KNN is also very important for image classification as a part of the pipeline design. The other supervised shallow learning is the regression. Linear regression is the way to predict the value of dependent variable from the independent variable. It can be univariable. So, for example, the prediction of the chance of malignancy from the size of the nodule. It can be multivariate. For example, the chance of malignancy from the density and the size of the nodule. If you remember this formula from the high school, the linear regression will depend on the weight and the bias. The weight determines the slope of the line. The bias determines the location of the line. The linear regression learn how to derive the best line between the different variables to best classify them into 2 groups using the feature and using the cost function as I described in the past. This is the linear regression for single variant. For the 2 variable, the model is going to derive a plane rather than the line. Same thing is true for multiple, for 3 or 4 variables, but for human, they are very difficult to show them as the picture, but it is very easy task for the linear regression to derive a multiplanar border between different label data. So I'm going to pass this linear regression. One subtype of linear regression is binary logistic regression. This is opposite to the linear regression. The output is not number, but the output is a prediction. You get 0 or 1. When you have a linear regression, but the output is 0 to 1, that means you have a logistic regression. The logistic regression is the backbone of the neural network. I'm going to explain a little bit in a few seconds. So remember, the linear regression is not the same as logistic regression. Linear regression is for the numerical data, while the logistic regression is for prediction 0 or 1. Lasso, or the least absolute shrinkage and selection operation, is a subtype of the linear regression. In the training data set, you may get this line. When you look at the real world, you can see that the real data is not matching perfectly to that line. So the lasso is the way to change the slope of the line to slightly improve it to fit better to the real world. And that's the changing the slope of this line, which now fitting much better to the real world. The act of lasso is converting the data and least important data to the 0. So that's going to delete much variable, and it's only going to keep the most important data. And this is the fact of feature selection. As a byproduct of the lasso, we can select the most important feature. And lasso these days is the most important feature selection model in the radiomics. For radiomics, we are going to have hundreds of features. For feature selection by lasso, you are going to select the most important 10 feature, and when you train the model on these 10 selected, your model is going to be very robust without any overfitting. Support vector machine is the other shallow learning, belong to the supervised model. The act of support vector machine is to derive the best and widest border between the samples, which are these data, which are blue and red in color. Support vector machine is deriving finding the widest border between these two samples. Very common machine learning model at the end of convolutional neural network for classification of images to different classes. Decision tree is the other shallow learning model. Decision tree is the learning which question to be asked. We have root, internal node, and leaf node. At each point, for example, if you are going to classify a long nodule to the malignant or benign, when you train the model over the time, the model learn to ask the size at the first question, the presence of speculation, the second question, and the density of the nodule as a third question, and so on. Then, based on the answer it gets from the data and the features from the nodule, it's going to classify this nodule to the benign or malignant. As you can see, decision tree is one of the models in the AI which is partially transparent. It's not completely black box. So that's the end of shallow learner. Besides shallow learning, we have different methods to improve the quality and accuracy of machine learning. There are ensemble methods. We are going to combine different models to each other to increase the accuracy. The most important are number one, bagging. In bagging, we are going to train different models on the data set, but for each model, we are going to manipulate the data set. We are going to remove and replace the data set several times, and we are going to train different models. For example, on this one, we deleted the red color, but we put 3 green color. In this one, we put 2 green and 2 blue, and so on. So we are going to train different models, actually from the same data set, but with some manipulation. When you combine these models to each other, you get the more important, the powerful model from the combination, and this act is calling bagging or bootstrap. When you run bagging on top of decision tree, is calling bagging tree. And one type of bagging is the random forest. This is one decision tree. You saw one example of decision tree for the long nodule. However, if you have 100 patients, but you develop different morphology and design of the decision tree for that data set, for each decision tree, you manipulate the data, you remove some of the patient and replace them with this two repeated patients, the same as color that I showed on the other slide, you will have different design of the random of the decision tree for the same data set. When you combine these decision tree to each other, you will have a robust model by name of random forest. Random forest is also very important model in the image classification in radiology. Eventually, you are the third technique for the improving the prediction accuracy is boosting. Boosting is the way of combining several different weak models to each other and make a robust model from different type of the weak learner and weak applications. So that's the end of ensemble methods. So you know the difference between the deep learning and shallow learning. Deep learning models are able to work on the raw data, while the shallow models, they have to be fed by the extracted features. They cannot work on the raw data. Now we are looking at the machine learning and deep neural network very quickly. The basic neural network is multi-layer perceptron. Perceptron is contain different input data, some hidden data in between, and then output layer. Each node is essentially a logistic regression. It gets information from the previous node, it processes information, it transfers it to the next layer, the same as neurons in human. So those are the linear logistic regression. It has different weights from the previous neurons. It has a fixed number, which is called bias. So it gets data from the previous, analyze it in association with bias. Then it's going to be activated. The activation, the same as neuron, is 0 or 1, everything or nothing. And the output depends on the type of logistic regression. If it's just classical logistic, output is 0 or 1. In TAND, it's -1 or +1. Or on ReLU, it's 0 or it's a line with 45 degree, and so on. And you can see we can have different design of the neural network. During the training session of neural network, every time we provide the data to the neurons and the models, the model is going to work on it and look at the actual prediction compared to the real world and see the performance. Every round of presenting data to the neural network is called epoch. The softwares that compare the prediction to the real world is going to call the backpropagation. And there are many softwares that are going to fine-tune every single neurons in the way that for the next round and next epoch, the performance is slightly improved for prediction. Running the multiple epoch and by fine-tuning of each node by backpropagation, eventually the performance is high enough and we call the model is trained. The same as the shallow learning, we have got ideal case, overfitting and underfitting curves in the neural network as well. So that's the overfitting. One policy to fight the overfitting is stopping the learning. If you stop the learning at this point, there is not much overfitting. If you continue learning, overfitting is much higher. The other type of regularization to fight the overfitting is augmentation. Very common in the radiology. You can add noise or you can change the angle of images. Easily you can multiply the data set by 100 times and to fight overfitting. Dropout is the other thing that you can use in the neural network training. Dropout means you turn some nodes on and off during the training. So during the training, only a part of nodes are on. The same as exercising in the mountain, but in the real match, in the Olympic, all of the nodes are going to be on. This is drop out and drop on. That means the training the model in the hard situation, but run it in easy situation, and it can fight the overfitting in the real world. So why we use convolutional neural network while we have perceptron, which is neural network? Because of the speed of computer. This image contains 5012 by 5012 pixel and 257 Hounsfield unit. That's the 67,000. Suppose we have each patient have 100 image, and only we have 100 patient. We know that each node has hundreds and millions of the bias and weight. It's going to be equal to 6.7 by 10 times 7. This number is so huge, even supercomputers at this time, they cannot handle this number. So the convolutional neural networks are the technique to help the neural network and perceptron to image detection. By convolutional neural networks, we are going to convert the image in the simple way that is understandable and easier to the neural network. We do by repeating convolutional layer, nonlinear layer, and max pooling or min pooling layers for different types. So convolution is actually multiplying the image and pixels to a filter. By selecting the filter, we can enhance something in picture. For example, if you multiply this image to this filter, it's going to enhance the horizontal line and convert all of the other lines to 0. This filter is going to enhance the horizontal line. You are going to use different filters or kernels. Then you will have, if you use 3 filters, you are going to have 3 images from 1 image, but every single image is much easier and simpler in comparison to the first image. Then we are going to implement a ReLU, which is a logistic regression, again, to make the images even much more simple. By one convolution, by one ReLU application, image is is simple. Now with max pooling or min pooling, we are going to reduce the size of picture. For example, for max pooling, we are looking at 4 adjacent samples or pixel. We are going to select the largest one. 1, 0, 1, 0, the largest one is 0. It goes this one. For these 4, the largest number is here, it's 2.5, so the number would be this one. Again, we are going to reduce the size of the image. So by multiple times of convolution, ReLU, and max pooling, again, convolutional ReLU, max pooling, we are going to increase the number of images, but they decrease the complexity of image. At some point, the images are so easy, you can feed them to the convolutional neural network. So that's the basic concept of convolutional neural network. At this time, there are many types of convolutional neural network, depend on the design. Every day, you see different types going on. Usually, the more recent, the best the performance of the convolutional neural network. Most of the time for image classification, you can use all of these open source convolutional neural network, and you can train them on your data set using this traditional model and retrain them on your data set is called transfer learning. Transfer learning is very common in your radiology samples. This convolutional neural network has been trained on the general data set. They are very good for classification of cat versus rabbit versus houses and so, but they cannot classify GBM from metastasis. To use it for differentiation of GBM versus metastasis, you can use it, you can modify it and retrain it on top of your data set for your design and your application. One subtype of convolutional neural network is very important for segmentation in radiology by name of UNet. UNet does this exactly the same convolution, max pooling, and ReLU, the same as convolutional neural network, but at some point, it's going to do the opposite. It's going to combine multiple small images. So from here to here, we are going to create multiple simple images from one image. Now, from this point, we are going to go backward. We are going to combine multiple small images to a larger image. At this point, we will be able to put the segmentation or the area of interest. Units are very robust for the segmentation task at this time. And I mentioned the task of transfer learning as well. This is the transfer learning when you obtain a traditional or open source, for example, ResNet, convolutional neural network. You copy it, you modified it, and train it on your data. You should say that you are retrain it on your data. Then the model is able to predict the chest pixel for long masses versus normal chest pixel. So that's the end of my topic. For your homework, please read 10 medical AI paper, preferably radiology. Now look at the design and see if you can understand the design. Look at the terrain validation and the test data set. Look at the models. How is the evaluation internally and externally? Which strategy was used to avoid the overfitting? Which generalization strategy was used? And see if you understand the performance metric in the paper or not. Thank you very much, everybody. That's the basic concept of radiology, very superficial conceptual data regarding the AI in medicine, especially radiology. Thank you, everybody, and have a good day.